The reported results show the reinforcement learning agent achieving 38.9 minutes, outperforming the genetic algorithm in this benchmark. The most interesting point is qualitative. The agent can learn behaviors that were not explicitly programmed, like preemptive mode switching or strategic waiting for a high-value dual opportunity. That emergence is what makes reinforcement learning attractive in dynamic operational settings. This comparison puts all methods on the same scale. Dynamic programming is optimal but computationally expensive. The heuristic is extremely fast but less efficient in time. Genetic algorithms provide a strong middle ground, better quality at moderate compute. Reinforcement learning can reach very high performance, but it requires training investment. This slide is about decision-making. Choose the method that matches your constraints and objectives. Here is the practical rule of thumb. Use dynamic programming when the instance is small and optimality truly matters. Use a heuristic when real-time speed is the priority and the instance is large. Use a genetic algorithm when you can plan offline and want better quality than a heuristic. Use reinforcement learning when you face recurring decisions in a changing environment, and you can afford the upfront training effort. Method selection is fundamentally a trade-off between time, scale, and optimality. Real terminals are not clean textbook environments. Arrival times are uncertain, equipment fails, weather disrupts operations, safety rules are strict, and systems must integrate with terminal operating systems. Models must therefore be robust and adaptable. Also, solutions must be explainable to operators and planners, because trust and adoption are as important as mathematical optimality. The single crane lift sequence problem is a starting point. Realistic extensions include multiple crane coordination, dynamic arrivals, stochastic service times, energy-aware optimization, and interference avoidance. Each extension adds constraints and objectives, but the core principle remains. Define the right state, model the right costs, and apply the right decision strategy for the scale. These exercises reinforce Tier 1 thinking. You are asked to formulate the complete dynamic programming recurrence for a new instance, using given weights, handling times, setup time, and dual constraints. The goal is to practice writing complete mathematical models and to understand how constraints are evaluated step by step in an exact optimization framework. These questions ask you to implement the WSPT heuristic, compute priority scores, and produce the resulting sequence for a larger instance. You are also asked to compare multiple constructive heuristics and explain which performs best and why. This reflects real practice. Engineers often compare several fast rules before choosing what to deploy. Here you design a genetic algorithm, define the chromosome, crossover and mutation operators, set population size and rates, and analyze convergence behavior. You also compare with simulated annealing. The purpose is to become fluent in global search strategies and understand how they trade computation time for solution quality. These exercises focus on reinforcement learning system design. You define a state representation, specify a reward, choose a network architecture, and set training hyperparameters. You also compare deep Q network variants. The key takeaway is that reinforcement learning success depends heavily on problem framing, especially state and reward design, before you ever start training. The main lessons are clear. The problem is NP hard, meaning it is computationally difficult in the worst case, but it becomes tractable with the right toolbox. Dynamic programming provides optimality but does not scale. Heuristics provide speed. Metaheuristics provide better quality at manageable cost. Artificial intelligence and reinforcement learning can provide adaptive policies when conditions change. And in the real world, robustness and integration are essential. To close, our goal was to sequence crane lifts to minimize make span while respecting constraints. Tier 1 gave a complete mathematical benchmark. Tier 2 gave fast operational heuristics. Tier 3 delivered near-optimal solutions through global search. Tier 4 showed how learning-based methods can adapt and improve over time. The best method depends on instance size, time pressure, and how much optimality you truly need.